Good morning, friends. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. As a continuation of the last lecture, that is the maximum likelihood estimation, we are today going to continue the same with some more extended addendums. Okay, let us look into the continuation of maximum likelihood estimation. First of all, that means today we will see some more examples on maximum likelihood estimation and also how it is useful in machine learning. These are the major things we are going to see in today's lecture. The goal in maximum likelihood estimation is to find the optimal theta by maximum the likelihood. That is, when you have a data set, huge data set with columns x1, x2, so on, xn. Okay, and there are some features missing, like some xk is missing, and xl is missing between 1 to n columns. There are two features are missing. You want to estimate them. Please catch my word, estimate. You want to estimate those features which are missing, xk and xl. Okay. Now for that, first you will observe after plotting these data points which are available, you will observe their progression. Suppose their progression is like that, then you will feel that the normal distribution will be best suitable because it is like reverse bell shape. The progression is like increasing and then decreasing. So depending on the progression, you will fix a probability distribution. Then you will fit a function for parameter. Suppose here we consider parameter, we fix sigma as some 1, and then we'll take mu as parameter which is to be maximized. Then our function will be L of mu, which is called likelihood function of mu, nothing but pi I is equal to 1 to n n of xi mu sigma is 1 we fixed. Okay, then we'll try to maximize this function. That means we will try to find the maximum possible value of mu. That means we will maximize this function and we'll find the maximum value of mu, and with that help of that mu, we will fix the function n of x comma mu comma 1, and with that we will find xk and xl. With this function we will find xk and xl. This is called maximum likelihood estimation. Okay, now in this maximum likelihood estimation, our objective is to maximize the theta, that is optimal. Optimal means to maximize the theta. Here we call mu, generally we call it as theta. So that is the objective of that function. In practice, we maximize the log of the likelihood, but generally the MLE of theta may or may not be directly feasible for applying mathematical process. That means for finding maximization, differentiation, integration, it may not be feasible. Then we will apply log. That is what he is mentioning. That is called log likelihood. Okay, this is about small recollection over the maximum likelihood. Now, yes, now we have seen this, and see here, you are observing a graph. Let me comment once again. The goal in MLE is to find the optimal theta by maximizing the log likelihood, as I said, and in practice we maximize the log of the likelihood, okay, in order to make the mathematical process as simple and as fast as quick as possible. That's all. Now we are going to see a graph here. Please see the graph. Are you observing this graph? Here we have drawn the function of the likelihood function of y given theta. Okay, that means we have plotted the theta values over there, theta values over x-axis, and we found the values of the function p of y comma theta, and we plotted them on y-axis. Then we are observing this graph. Okay, now let me show you once again the graph. Yes, this is the graph where this red line is built by theta comma p of y comma theta. Okay, where theta values are on x-axis and the likelihood function values are on y-axis. Now, the thing is, does the application of logarithm will affect the maximum or minima of the function? Because see here, what is maximum minima? You can see that there are peaks of, if you see this as a series of mountains, there are lows and ups and lows and ups, lows and ups. Okay, right. So you are observing so many heights and downs. Among them, one of them will be highest peak or highest pinnacle, that is called maxima, and one of them will be the lowest thing, that is called minimum. So now the thing is, yes. Now the thing is, on p of y comma theta, when we apply logarithm, does the maximum or minimum will affect? No, it doesn't affect, because logarithm is always monotonic. Logarithm is always monotonic. What do you mean by monotonic? Simple. As x1 less than x2, log x1 is always less than log x2. So it preserves the order. That means when the succeeding value is more than the preceding value, then automatically logarithm will also in the same order. That is x1 less than x2, log x1 less than log x2. That is why there will be no effect on the maximum. That is why we could apply log on both sides. That is why log likelihood can be suggested instead of maximum likelihood. Okay, now here we are observing two things. Taking log doesn't affect the optima, since log is a monotonic function. Monotonic, just have told you, x less than y means log x less than log y, that is monotonic. Okay, and leads to simpler algebra and calculus. As you know, log mn is equal to log m plus log n. That means logarithm makes product into addition. Where addition is simple or multiplication is simple, addition definitely. And log m by n is nothing but log m minus log n. You can tell whether division is simple or subtraction. Obviously subtraction. That means logarithm converts division into subtraction. Similarly, log m power n is equal to n into log m. That means it converts a big power into simple product of two numbers. That is one advantage. So all these also logarithm, derivative of logarithm is very simple. So all this makes that it is very simple. Logarithm is always very friendly for algebraic as well as calculus operations, and also numerical stability. That means you could you could precisely tell the limits where, for greater than between 0 and 1, logarithm will be yields to a negative number, but greater than 1, logarithm will always leads to positive. That means numerical stability is there. So all these makes a log likelihood a beautiful estimator for maximum estimation of theta. That's what this slide is designed to communicate. Okay, now yeah, so in brief, our challenge is to maximum likelihood. That means to find the maximum likelihood of theta. That means you will find, first you will construct the likelihood function of theta. Then you will maximize that. That is as equal as constructing the likelihood function and applying log, and then finding the maximization. Both are equivalent. And finally, theta would be this value. Okay, the final maximum likelihood value will be theta will be the summation of all these logarithms. You could tell. Okay, this is what in simple you can explain about the maximum likelihood estimation. Now, here one more important thing is, why can't we see it as a minimization problem? Why you are always a maximum likelihood estimation? Yes, that means you are always seeing it as a maximization. The objective is maximization of theta. What can we see in others from other side? Can we see it as a minimization? Yes, we could also represent it as a minimization problem. Here you could see, after seeing the log likelihood function. Okay, and if you instead of this, if you consider this function, okay, if you consider this function, the minimum value of theta yields the maximum value of theta here, because you know that when log p of x is maximum at some alpha, then minus log p of x will be minimum at the same alpha. This is the law we know in our maximum minima. I think you might have come across in your intermediate while doing maximum minima. Log p of x is a function which has a maximum at alpha. Then automatically minus log p of x will attain its minimum at alpha. In that, by taking that as a support, we could see the maximum likelihood estimation as a minimization problem also. Not only maximization, you could also see it as a minimum. But generally, we'll always do in the view of maximization, of course. But if you want, you could do it on a minimization basis. Okay. Now, here we are going to see a small example of maximization of likelihood function. Consider a sequence of m coin toss outcomes. That means you are tossing a coin for n times. First time like that, n tosses. Okay. And the observations here, because n tosses, you are writing n observations here. You'll write 1. If it turns into head, you'll write 0 if it turns into a tail. Okay. Now, each yn is assumed generated by a Bernoulli distribution with a parameter theta. That means now, because there are two possible outcomes, head and tail, that means two possible outcomes. You know, the distribution which deals with two possible outcomes is Bernoulli distribution. So, because Bernoulli trials, let us recap, finite number of sequence of trials which are independent of each other, and each trial consists of only two possible outcomes, namely success and failure. That the success is head and the failure is tail. That is why Bernoulli distribution suits here. Okay. So now the Bernoulli distribution parameter is theta. Okay, where theta belongs to 0, 1, because 0 means tail, 1 means head. Okay, only that means you could have to write it as like this, 0, 1. Okay. Now, okay, here we want to maximize the value of theta by using maximal likelihood estimation. For that, we will construct. First, let us start with what is Bernoulli distribution. Bernoulli distribution is theta power n 1 minus theta power, okay, theta power n, or theta into 1 minus theta. You could write it as only one trial we are considering, theta into 1 minus theta. Okay, so no, we will consider, yes, we have to consider Bernoulli of theta comma yn, which could be theta power yn into 1 minus theta power 1 minus theta power 1 minus yn. Okay, that means if in yn trials, the possibility would be theta power yn into 1 minus theta power 1 minus yn. Okay. Now, after considering this, I'd like to do some calculations. So, theta power yn 1 minus theta power 1 minus yn. Okay. Now, I apply log on both sides. Log on both sides. This is b of yn comma theta. Applying log on both sides. What happens? Log Bernoulli distribution yn comma theta is equals to, log mn, log m plus log m, log m plus log n. Right? Now, log m power n. Log m power n means, n log m. Log m power n. That means n log m. That means you will get yn log theta plus 1 minus yn log 1 minus theta. Okay. And this is true for all Kaplan observations. So, we could sum it as 1 to n. And this is our log likelihood function. Okay. Now, I'll write the end result once again. That means we have obtained the log likelihood of the function as summation I is equal to 1 to n yn log theta plus 1 minus yn log 1 minus theta. Okay. After obtaining this, we want to find the maximum possible value of theta, right? We want to find the maximum possible value of theta. For that, we will differentiate, we will partially differentiate with theta. That means dou by, or you can write differentiate, no issue, d by d theta of log b of theta. Okay, that is equal to, see here, log theta. Log theta, what is the derivative of log x? 1 by x. So, log theta derivative will be theta, that is summation I is equal to 1 to n yn by theta plus, what is log x derivative 1 by x? So it would be minus 1 minus yn by 1 minus theta. Okay, this is our log b of theta after derivative. That means after calculating the derivative with respect to theta. Now, equating it to 0. Equating it to 0 means 1 by theta into summation yn is equal to 1 by 1 minus theta into summation 1 minus summation yn. Okay. Summation 1 I is equal to 1 to n. That means it becomes 1 by theta into, if you divide with this n, that is y bar, is equal to 1 by 1 minus theta. That means into 1 minus divided by n, that means y bar. Okay, so 1 by theta into y bar is equal to 1 by 1 minus theta into 1 minus y bar. Okay, now by doing cross multiplication, by doing cross multiplication over here, what we get, 1 minus theta into y bar is equal to theta minus theta y bar. Okay, that means y bar minus theta y bar is equal to theta minus theta y bar. Theta y bar cancel. What is theta? Theta is equal to y bar. So what we obtained, finally applying maximum likelihood estimation using the logarithm, we obtained that the required theta value will be maximum if at the mean of all these y values, that is y1, y2, so on, yn, y1, y2, yn, the mean will be the maximum possible. Okay, that is what we arrived. So by using this maximum likelihood estimation, we estimated that the maximum possible value of theta will be the arithmetic mean of the observations or n data points. That's what here we have established. Here you could see the difference between likelihood and probability. Likelihood refers to the past events with known outcomes, whereas probability refers to the occurrence of future events. Likelihood is about thinking about the past occurrences. What is the likelihood of the thing which is happened like that? Okay, and here the probability is about it refers about the occurrence of future event. That means what is the chance that something is going to happen. It deals about the happened. It is the probability deals about the things going to happen. Here I flipped a coin 10 times and obtained 10 heads. What is the likelihood that the coin is fair? That means here the things game is already done. He is telling what he has done. He flipped 10 coins and the results are 10 heads. What is the likelihood that the given coin is fair? There is no cheating in the coin. Okay. That means it is about already happened again. 10 coins are tossed and 10 heads are obtained. Then he is asking a query about the coin, that is about likelihood. Okay. Now here another question. I flipped a coin for 10 times. What is the probability that of it landing head or tail every time? Suppose if I tossing a coin for 10 times, what is the probability that it will use either head or tail? That means it is about the future. The game is not yet done. It is going to be happen. And you are trying to predict. That is about future. This is called probability and this is called likelihood. So in likelihood about past happened and probability about happening in the future. And the likelihood is about maximizing the parameter. Probability is about finding the probability of happening of an outcome. Okay, that is the major difference we could see. Likelihood doesn't add up to 1. Here if you add the likelihoods, it need not be 1, but probabilities always add up to 1. That means whatever the events that is going to happen in the thing, all we add it will get 1. Okay, that is these are the major differences between the likelihoods and the probability. Okay, when the probability of a single coin tosses is low, of range 0% 10%, logistic regression is a model for binary classification in practical application. Here he is listing one for practical model which distribution is suitable. For a practical situation like probability of single coin toss is low in the range of 0, very low, then logistic regression is a model for binary classification of real time. That's what he's telling. Okay, and a probability distribution for the target variable must be assumed and followed by a likelihood function that calculates the probability of observing outcome given the input data and the model. The function can be optimized to find the set of winners. Results in the sum of likelihood ever trained in the data set. That means he's just summarizing the things. That means when you see a data set and when you are missing with some features, you want to extract them, you want to estimate them, then first you have to observation the progression of the available data points, and basing on that you have to pick up a probability distribution which suits that data, and for that distribution there will be a parameter you have to fix and you have to try to maximize that parameter. After getting the maximum possible parameter value, then you have to fix the function, the density function, and by using that you have to predict the missing features. That is what he's saying. Okay. Now I'd like to conclude this lecture with a small example, one more small example. Suppose I'm taking a function uh, whose density function is alpha into e power minus 3 alpha x for x greater than or equal to 0 and 0 for otherwise. That means for negative. Now I'd like to find the maximum possible value of alpha because alpha is a parameter. Alpha is the parameter. I would like to find maximum possible value of alpha. Okay, for that I'll take, okay, f of xi comma alpha as alpha e power minus 3 alpha xi. That means I am considering only finite data points x1, x2, so on, xn. So I am multiplying this, then I will get pi f of xi comma alpha is equal to 1 to n. That is pi I is equal to 1 to n alpha into e power minus 3 alpha xi. Okay. Now applying log on both sides. I am going to apply log on both sides. Let us see what happens. This is first I call it as likelihood function of alpha. Now, in order to make it mathematical friendly and mathematical feasible, I am going to apply log on both sides. So log on both sides means this becomes logarithm of L of alpha is equal to, when we apply log, log mn. What does it mean? Log m plus log n. Log mn means log m plus log n. Now, by using that, it's a product. So it becomes log summation. The product becomes summation I is equal to 1 to n alpha into e power minus 3 alpha xi. Alpha into e power minus 3 alpha xi. Okay. Now, you can take alpha out. So 1 minute when we apply log, sorry, let the small correction. When we apply log on both sides, it becomes log of L of alpha is equal to summation I is equal to 1 to n log alpha plus log e power minus 3 alpha xi. This is what we get. Okay. Now see here, for further next simplification, I'm just cleaning the board to write down the next steps of simplification, and our mission is to obtain maximum possible value for alpha. Okay, so after applying log mn, log m plus log n, so we have got this. Here log alpha is constant, so we can write it as log L of alpha is equal to log alpha comes out summation I is equal to 1 to n, 1 remains in, and log m power n. What is log m power n? N log m. N log m. That means you will get minus 3 alpha xi into log e base c. Okay, after applying log mn, n log m, that means we get this. Now, log alpha, you are adding 1. How many times? 1 plus 1, 2. 1 plus 1 plus 1, 3. Like that you are adding for n times. That means it becomes n plus log e base is always 1. Log e base is always 1. So it becomes minus 3 alpha xi. This is the function log of L of alpha. Okay. Log alpha into n minus 3 into alpha xi. Okay. Now, log L of alpha is equal to log n minus 3 alpha into xi. Okay. Log L of alpha is equal to log alpha into n minus 3 alpha xi. This is what we got. Now let us differentiate with respect to alpha. Differentiate with respect to alpha. Then this would be the log likelihood function, that is small l of alpha. I'm just denoting it as another function small l, okay, which is called log likelihood function L of alpha. Here we are differentiating with alpha, so n is a constant, n comes out. Log alpha derivative, log x derivative with respect to x, 1 by x. Log alpha derivative with respect to alpha, 1 by alpha, minus alpha derivative with respect to alpha, 1, 3xi. So what you got? L alpha is equal to n by alpha minus 3xi. Now let us equate it to 0. Then n by alpha is equal to 3xi. Now we want to find alpha, that is alpha is equal to n by 3xi. Okay, here uh, summation we forgot. Summation xi means summation xi, here we forgot. Summation xi means summation xi. Okay, summation xi. Then 1 by alpha is equal to 3 into summation xi by n. 1 by alpha is equal to, sum of all observations by number of observations becomes x bar. So alpha is equal to 1 by 3x bar. That means for the density function, f of x is equal to alpha into e power minus alpha into e power minus, what is the function? Alpha into e power minus 3 alpha x. Okay, the maximum possible value for alpha is 1 by 3x bar. 1 by 3x bar. That means the mean of this density function, 1 by 3 times of the reciprocal of the mean, is the maximum possible value of all of the parameter alpha. That's what we proved by using maximum likelihood estimation. Okay, now we have seen few examples how to use maximum likelihood estimation to find out the maximum possible alpha. Okay, here you could learn the last class we have seen this for normal distribution, how to find maximum likelihood estimation. Okay, and the properties of maximum likelihood distribution. Okay, all these things we have seen in the last class. Now the thing is, finally I'd like to conclude the lecture with one small thing, that the maximum likelihood estimation role is very vital in machine learning, because to extract the missing features, in a data set x1, x2, so on xn. Okay, we have to use probability distribution. Okay, and when we use probability distribution, definitely it will be associated with a parameter alpha or theta, and if we maximize the theta, the estimation would be as better as possible. That means as accurate as possible. That's what. So first we will try to maximize the parameter theta. After maximizing theta, we will fix the function f of with the maximum value theta and the variable x. Okay, then we will use that to estimate f of theta comma xk, or whatever the missing feature. So in this way, it plays a very important role in machine learning. That is why maximum likelihood estimation is very important. Okay, in the next class we will see some examples on log likelihood estimation. That means a support part of maximum likelihood estimation is log likelihood estimation, which we will discuss in the next class. And thanks for your patience listening. Now I am signing off. We'll meet in the next class on log likelihood estimation. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.